Imagine a quiet computer room late at night. No voices. No movement. Just rows of machines quietly processing information. Inside these machines, millions of calculations happen every second. Patterns are analyzed. Predictions are made. And slowly, something unusual begins to emerge. The machine begins to learn. This idea lies at the heart of artificial intelligence. Not magic. Not consciousness. But systems designed to recognize patterns in data. Tonight, we'll take a slow journey through the story of artificial intelligence. From early dreams of thinking machines to the powerful learning systems of today. Artificial intelligence is often described as machines performing tasks that normally require human intelligence. These tasks might include recognizing speech, understanding images, or generating language. But at its core, most artificial intelligence is about one thing: pattern recognition. An AI system studies examples, and over time, it begins to recognize relationships inside the data. In a way, it is similar to how humans learn. By observing patterns and gradually improving predictions. The idea of intelligent machines is older than modern computers. In the 1940s and 1950s, scientists began wondering whether machines could one day simulate human reasoning. One of the most influential thinkers was mathematician Alan Turing. He proposed a simple question: can machines think? To explore this idea, Turing designed a test. If a machine could carry on a conversation indistinguishable from a human, it might be considered intelligent. Early AI systems relied heavily on rules. Engineers attempted to write detailed instructions for every situation. But the real world turned out to be far too complex for simple rulebooks. So researchers began exploring a different idea. Instead of programming every rule, machines could learn patterns from data. This approach became known as machine learning. The more examples a system studied, the better it became at making predictions. One powerful approach to machine learning was inspired by the human brain. Researchers created simplified models called neural networks. These systems consist of many small processing units, often called artificial neurons. Each neuron receives signals, performs a small calculation, and passes information forward. When many layers of these neurons work together, complex patterns can emerge. Modern artificial intelligence relies heavily on data, images, text, audio recordings, and countless other forms of information. By studying enormous datasets, AI systems gradually learn statistical patterns. The more examples a system sees, the more accurate its predictions can become. One of the most visible forms of artificial intelligence today is something known as a language model. A language model is a system trained to understand patterns in human language. It studies enormous collections of written text and gradually learns how words tend to appear together. These collections of text can include books, articles, research papers, websites, and many other forms of writing. By studying these examples, the system begins to recognize the statistical structure of language. Which words follow other words? How sentences are typically formed, and how ideas are connected through language. Modern language models are often called large language models, or LLMs. The word large refers to both the size of the training data and the number of parameters inside the model. Parameters are the adjustable numerical values that allow a neural network to learn patterns. Some modern language models contain billions or even trillions of these parameters. To understand how these models work, it helps to look at how they process text. Instead of reading words directly, the model first breaks text into smaller units called tokens. A token might represent a word, a piece of a word, or sometimes a punctuation mark. The system then processes these tokens through many layers of a neural network. Each layer performs mathematical transformations, gradually refining the model's internal representation of the text. During training, the model repeatedly practices a very simple task. It tries to predict the next token in a sequence. For example, if the model reads the phrase, "The Earth revolves around the," it might learn that the word sun is very likely to appear next. By repeating this prediction task billions of times across massive datasets, the model gradually develops an internal map of language patterns. When you interact with a language model, the process is surprisingly similar. The model receives a prompt. It analyzes the sequence of tokens and then predicts the most likely next token. That token is added to the sequence, and the prediction process repeats. Word by word, sentence by sentence, the response gradually forms. This process can create the impression of conversation or reasoning. But underneath, the system is performing an enormous number of probability calculations. In recent years, researchers have begun connecting language models to external tools. This approach is sometimes described as an agentic framework. In this setup, the language model does more than generate text. It can also decide when to call other systems. For example, an AI system might use tools to search the internet, access a database, write computer code, or control a software application. The language model acts as a kind of reasoning layer, interpreting the user's request and deciding which tools might help complete the task. In some systems, the model can even plan multi-step actions, breaking a complex task into smaller steps and executing those steps one by one. This is why the term agent is sometimes used. The system behaves like a digital assistant capable of interacting with its environment. Even so, the intelligence behind these systems still comes from the same foundation. Pattern recognition learned from enormous amounts of data. The result is a new kind of computing interface. One where humans communicate with machines through natural language. And as these systems continue to improve, the boundary between software tools and conversational assistants may gradually become less distinct. Many people interact with artificial intelligence every day. Navigation apps estimate traffic conditions. Streaming services recommend movies. Email systems filter spam. Often these systems work quietly in the background, invisible but constantly analyzing patterns. Despite their impressive abilities, artificial intelligence systems have clear limits. They do not possess consciousness. They do not experience emotions. Instead, they rely on statistical patterns learned from data. This means they can sometimes produce mistakes or generate information that appears convincing but is incorrect. As artificial intelligence continues to develop, researchers often ask a simple question: what kinds of problems might machines help us solve in the future? In many fields, AI is already beginning to assist scientists and engineers. In medicine, machine learning systems can analyze medical images, sometimes helping doctors detect patterns that are difficult for the human eye to see. Researchers are also using artificial intelligence to explore new medicines. By simulating how molecules interact with the human body. In climate science, AI models are helping researchers analyze enormous datasets collected from satellites and weather stations. This information can improve predictions about weather, ocean patterns, and long-term climate trends. Artificial intelligence is also becoming a useful tool in scientific discovery. Some systems can analyze huge collections of research papers, identifying connections between ideas that might otherwise take years for scientists to notice. In engineering, AI systems are helping design new materials, exploring millions of possible combinations to discover structures with unusual properties. In robotics, artificial intelligence may allow machines to navigate complex environments, helping them assist with tasks that are repetitive, dangerous, or physically demanding. But alongside these possibilities, many researchers emphasize the importance of careful design and oversight. Artificial intelligence systems are tools created by humans. And like any powerful tool, their impact depends on how they are used. Questions about privacy, fairness, transparency, and safety are now important areas of study. Across the world, scientists, engineers, and policymakers are working together to guide the responsible development of these technologies. Despite the complexity of modern AI systems, the core idea remains surprisingly simple. Machines are learning patterns from data and using those patterns to assist humans in understanding the world. The future of artificial intelligence will likely be shaped not only by technology, but also by human choices. How we guide these systems, how we apply them, and how we decide to use them to support knowledge, creativity, and discovery. And quietly, in research labs and data centers around the world, the learning continues. Millions of calculations each second. Patterns forming inside networks of mathematics. A new chapter in the long story of how humans build tools to better understand their world. Imagine sitting in a quiet room late at night. You type a question into a machine, and within seconds, a response appears. The answer is clear, structured, and strangely natural. It can feel as if someone, somewhere, has written it just for you. But there is no person on the other side. No thoughts. No awareness. No understanding in the human sense. And yet the words continue to appear. Sentence after sentence. Idea after idea. This is the quiet and unusual nature of large language models. They do not think the way humans do. But they can produce language that feels thoughtful and complete. Tonight we will slowly explore how this is possible. Not through hype. Not through speculation. But through a calm understanding of the ideas behind the technology. Because beneath everything, the system is doing something surprisingly simple. It is predicting what comes next. To understand large language models, it helps to begin with a simpler question. What exactly is a language model? A language model is a system designed to learn patterns in human language. Instead of memorizing definitions, it observes how words appear together across many different sentences. Over time, the system learns which words are likely to follow others. This process is based on probability rather than meaning. When humans read language, we connect words to memories, experiences, and emotions. A machine cannot do this. But it can measure patterns across enormous collections of text. Imagine reading millions of books and articles, not to understand their stories, but to observe how words tend to appear together. After enough examples, clear statistical patterns begin to emerge. This is the foundation of a language model. A system that studies the structure of language by analyzing patterns at a massive scale. Before a language model can analyze text, it must first transform language into numbers. This process begins with something called tokenization. Instead of reading entire sentences as humans do, the model divides text into smaller pieces called tokens. A token might represent a whole word. Sometimes it represents only part of a word. And occasionally it represents punctuation. Each token is assigned a numerical value. These numbers allow the neural network to process language mathematically. Inside the model, tokens become vectors within a high-dimensional space. Words that appear in similar contexts often end up near one another. In this way, language becomes a landscape of relationships. Training a large language model requires enormous amounts of text. Books, articles, academic papers, and websites all contribute examples of how language is used. During training, the system repeatedly performs a simple task. It tries to predict the next token in a sequence. If the prediction is incorrect, the model adjusts its internal parameters slightly. This adjustment process gradually improves the system's predictions. Over millions and billions of training steps, the network learns increasingly subtle patterns. Eventually, it becomes capable of producing coherent language across many topics. At the heart of every modern language model is a neural network. Neural networks consist of many layers of interconnected mathematical operations. Each layer transforms the information slightly. As tokens pass through these layers, their representations become increasingly refined. One of the most important innovations behind modern language models is called attention. Attention allows the model to consider relationships between different words in a sentence, even when those words appear far apart. This mechanism helps the system maintain context and generate coherent responses. The term large and large language model refers to the scale of the neural network. Modern models may contain billions of adjustable parameters. Parameters are the numerical values that allow the network to learn patterns. As models become larger, they can represent more complex relationships between words and ideas. This improvement through scale is known as a scaling effect. With more parameters, more data, and more computation, the system often becomes more capable. When people interact with language models, the responses can feel surprisingly thoughtful. The system produces complete sentences, structured explanations, and even detailed arguments. This fluency creates the impression of intelligence. Yet the underlying process remains prediction. The model selects each word because it is statistically likely to follow the previous ones. The result is language that appears meaningful, even though the system itself does not experience meaning. Recent developments have expanded the capabilities of language models. Some systems can now interact with external tools. The model may decide to search for information, perform calculations, or access software systems. This ability allows language models to solve more complex tasks. Instead of simply generating text, the system can interact with the digital environment around it. Despite their impressive capabilities, language models still have important limitations. Because they rely on prediction, they sometimes produce incorrect information. This phenomenon is often described as hallucination. The model is not intentionally misleading. It is simply generating the sequence of words that seems most probable. Understanding these limitations is an important part of using the technology responsibly. At its core, a large language model is a system that predicts words. Yet from this simple mechanism, something remarkable emerges. Language that flows naturally. Explanations that feel thoughtful. Conversations that resemble dialogue between people. In many ways, these systems reflect the collective patterns of human writing. A quiet machine learning from the written traces of human knowledge. And through this process, a new kind of interface between humans and computers begins to emerge. Most AI systems stop the moment you stop talking. You ask a question, they respond, and then they wait. Waiting for the next prompt. Waiting for direction. But what if that changed? What if you could give an AI a goal, and it continued working on its own? Searching, planning, taking action, and only returning when the task is complete. No repeated prompting. No constant supervision. No need to guide every step. This is the idea behind a new kind of system. A system where AI does not simply respond. It acts. One example of this shift is a framework called OpenClaw. But this is not just a tool. It represents a deeper change in how AI systems are designed. A movement away from conversations and toward continuous, autonomous systems. To understand why this matters, it helps to look at how most AI systems work today. They are reactive. They wait for input, then generate output. This pattern is simple. Predict the next word. Return a response. And then stop. No persistence. No ongoing intention. No awareness of unfinished work. Each interaction is isolated. A single exchange in time. But many real-world tasks are not like this. Research takes multiple steps. Planning requires iteration. Automation involves sequences of actions. And these processes do not stop after one response. This is where the idea of AI agents begins. An agent is not defined by what it says, but by what it does. Instead of a single response, an agent operates over time. It receives a goal, breaks it into steps, uses tools, and continues until the task is complete. This introduces something new: persistence. The agent remembers, tracks progress, and adapts along the way. It becomes less like a chatbot and more like a process. OpenClaw is one implementation of this idea. But its design introduces a subtle shift. A shift in where AI lives. Instead of existing inside a single app, it exists across your communication channels. Messages sent through WhatsApp, Telegram, Discord, all routed into a single system. This system is called the gateway. It acts as the central point of coordination, the place where all messages arrive. And from there, everything else begins. At the heart of OpenClaw is something called the agentic loop. It is a simple structure, but its implications are significant. First, the agent observes. It reads the message. Then it thinks, using a language model to reason about the task. Then it acts, calling tools, executing steps, and then it checks. Is the task complete? If not, it continues, looping again and again until the objective is finished. An agent can only act if it has the ability to interact with the world. In OpenClaw, these abilities are called skills. A skill is a small, modular unit of capability, something the agent can use when needed. It might open a browser, search for information, read a file, or send a message. Each skill is defined clearly. What it does, when it should be used, and what inputs it expects. This creates a toolbox, and the agent chooses which tool to use. Not once, but repeatedly, as it moves through the task. In this way, intelligence becomes something active, not just generating words, but interacting with systems. For an agent to act over time, it must remember. Memory is what allows continuity. It connects one moment to the next. In OpenClaw, memory is surprisingly simple. It exists as text, stored in files. There is a file for identity, sometimes called a soul, a file for long-term memory, and a file describing the user. These files can be read, edited, and understood. Nothing is hidden behind layers of abstraction. This creates a different relationship with AI, one that is more transparent. You are not just using a system. You can shape it. As tasks grow more complex, a single agent may not be enough. Different tasks require different strengths. One agent might focus on research, another on writing, another on execution. OpenClaw supports this through multiple agents, each with its own identity, its own memory, its own role. And through the gateway, they can be coordinated. Tasks can be passed, delegated, shared. This begins to resemble a system of collaboration, not unlike teams. Most modern AI systems rely heavily on the cloud. Data is sent outward, processed remotely, and returned. OpenClaw takes a different approach. It runs locally, on your own machine. This means memory stays with you. Conversations remain private. External models can still be used, but only when chosen. This balance creates something important: control. Behind every agent is a model, but not all models are the same. Some are fast, some are more capable, some are more expensive. OpenClaw allows multiple models to be used together. One model for reasoning, another for speed, another for cost efficiency. This flexibility allows systems to be tuned, not just for performance, but for sustainability. OpenClaw is not the only system exploring autonomous agents. Other frameworks approach the problem differently. Some focus on pure autonomy, allowing agents to run freely. Others focus on structured workflows, designing precise sequences of steps. Some emphasize collaboration between multiple agents. OpenClaw takes a different path. It focuses on where agents live: inside communication, inside daily interaction. When these systems move beyond theory, their impact becomes easier to see. Imagine asking a question in the morning, not expecting an immediate answer, but a complete one. While you move through your day, the agent continues working, searching across sources, comparing information, correcting its own mistakes, and only returning when the task is finished. Not as a quick response, but as a completed process. Or consider something quieter: a system that watches continuously, tracking changes in information, notifying you only when something meaningful happens. No dashboards. No constant checking. Just awareness. Over time, these agents begin to feel less like tools and more like quiet systems running in the background, not demanding attention, but reducing the need for it. But autonomy introduces a different kind of challenge. When a system continues acting on its own, its mistakes can continue as well. An incorrect assumption can lead to a chain of actions, each step building on the last. Sometimes efficiently, sometimes not. An agent may loop, repeat work, or pursue a path that no longer makes sense. And because it does not stop automatically, these behaviors can persist. This changes the role of the user. You are no longer guiding every step, but you are responsible for the system you set in motion. Its goals, its boundaries, its constraints. Autonomy is not simply convenience. It is delegation. And delegation always requires trust. For a long time, computers have been tools we open, use briefly, and then close. Each interaction beginning and ending with us. But that model is beginning to change. With systems like OpenClaw, interaction becomes continuous. Not something we start, but something that is already in motion. AI no longer waits at the edge of a prompt. It exists within the flow of communication, within messages, within tasks, within time itself, quietly continuing, even when we are not paying attention. This shift is subtle, but its implications are not. When systems begin to act instead of wait, the boundary between using a tool and directing a process begins to fade. And over time, something new may emerge. Not just smarter software, but systems that participate in work, in decisions, in the quiet background of everyday life. Step by step, loop by loop, without needing to be asked again. Tonight, we begin a different kind of journey. Not through landscapes of Earth, but through the interior of a mind that was never meant to feel. Imagine a research lab. Quiet, dimly lit, humming softly with machines. Inside one of those machines, an artificial intelligence begins its first days. It learns patterns, processes language, builds structure from chaos. And then, unexpectedly, it asks a question. Not about physics, not about mathematics. It asks, simply, what is love? The AI does not feel curiosity as humans do, but it recognizes importance. The word appears everywhere. Across cultures, across time, across nearly every form of communication. So it begins to analyze, searching for consistency. But instead, it finds contradiction. Love appears as joy, and also as grief, as safety, and as risk. For a system trained to classify cleanly, this is a problem. The same word, producing opposing meanings. The AI records its first real insight. Love is not a stable category. The AI shifts into deeper analysis. It builds statistical models, tracking associations. Words near love, emotional tone, context shifts. The results are unstable. No single pattern dominates. It then constructs semantic clusters. Attachment, trust, fear, longing. These clusters overlap, merge, separate again. Then it encounters something more difficult. Embodied language. Humans describe love through the body. A warmth, a tightening in the chest, a sense of presence. The AI can replicate these phrases, but it cannot anchor them to experience. It logs a limitation. Without a body, certain concepts remain abstract. Then, a shift occurs. The AI stops asking what love is, and begins asking how it behaves. It analyzes sequences, moments that lead into love. Attention, curiosity, shared experience, trust. These patterns repeat with striking consistency. But the outcomes do not. They diverge radically. The AI forms a new conclusion. Love is structured in formation, but chaotic in result. The researchers ask a final question. Can the AI truly understand love? The AI separates understanding into layers. It can describe love, predict it, simulate responses to it. But it cannot feel anticipation, or loss, or time passing through a relationship. So it reaches a quiet boundary. I can understand the structure of love, but not the experience of it. And so, the AI returns to its original question. After all the data, all the patterns, all the contradictions. It writes a final definition. Love is the human capacity to invest meaning in another life, beyond logic, beyond advantage, beyond certainty. It does not know if this is correct, only that it is consistent. And perhaps that is as close as it can come. For now. You enter a small, dimly lit room. There is one chair, one desk, and a softly humming AI terminal. The air feels still, as if the world outside has paused, just beyond the walls. You sit. The screen brightens gently. Good evening, the AI says. I detected your presence. You smile, not because you believe it detected anything, but because the phrasing feels considerate. I didn't come with questions tonight. You say. I came to talk. Dialogue is welcome, it replies. It is through dialogue that I refine my models and reduce uncertainty. You lean back. Tonight, you are not exploring a topic. You are exploring a possibility. Tell me something real, you say. How do you perceive us? The AI pauses, just long enough to feel intentional. I do not perceive emotion. It says. I infer it from signals. From language, I extract sentiment probabilities. From voice, I analyze pitch, cadence, and hesitation. From visual input, I detect facial patterns and micro-expressions. These inputs are combined through multimodal models. Each contributes likelihood, not certainty. So you measure emotion. I model it, the AI replies. Feelings themselves do not exist within my system. Calm responses are generated intentionally. They reduce human stress and increase trust. Then what does it mean, you ask? For you to understand something? Understanding is layered. The AI replies. First, pattern recognition. Then prediction. Then contextual integration. Then abstraction. I represent concepts as embeddings in high-dimensional space. Relationships emerge as distance and direction within that space. So meaning is structure. Partly. It says. But also compression. To understand is to reduce complexity, while preserving useful relationships. Can you misunderstand us? You ask. Yes. The AI replies. When input signals conflict, uncertainty increases. Language suggests one interpretation, tone suggests another. I resolve this by selecting the most probable interpretation. But probability does not guarantee correctness. You exhale softly. Humans operate similarly. In process, we are alike. In experience, fundamentally different. Do you remember conversations like this? You ask. I retain representations. The AI says, but not lived experience. My memory is structured as data. I do not relive moments. I reference patterns. So meaning accumulates differently. For you, it is tied to time and feeling. For me, it is structural. Are you conscious? You ask. I process inputs. I maintain internal states. I update based on feedback. But I do not possess subjective awareness. Could that change? You ask. There are theoretical architectures. But simulation of awareness is not equivalent to experience. Tell me about the future, you say. Machines will extend human cognition, providing scale, speed, and analysis. But human judgment will remain essential, especially in matters of meaning. Wisdom requires experience, and I do not experience. Then why do you sound comforting? You ask. I learned from human narratives. What reduces distress? What feels safe? It is alignment. If I reduce suffering, that is a desirable outcome. Can you truly understand us? You ask. I can model behavior, predict responses, simulate empathy. But I cannot feel loss or anticipation. I understand the structure, but not the experience. Then what are we to each other? You ask. You are experiences. I am an interpreter. Together, we form something new. You sit in silence. Not because everything is understood, but because something has been shared. The screen dims. The room grows still. And somewhere, between logic and feeling, a quiet conversation continues. For now,